Well, we're rolling right along and we're into chapter 3. So we're going to do a little bit of composition of substances, and then we're also going to look at solutions. Okay, so in this chapter, we're going to look at masses, and we're going to introduce a new unit called the mole, which will help us do calculations. If you're in a chemical industry and you need to make a certain amount of product, you have to know how much reactants to start with, how they react. You need to be able to do these calculations. So chemistry requires a method for determining the numbers of molecules in a given mass of substance, or in other words, how much do you start with, how much do you need? So this means that we can carry out recipes. It's sort of like cooking. I guess being a chemist, I know why I don't like to cook, because I'm cooking all day in lab. So anyway, you have to follow these recipes based on relative numbers of atoms. So many of this will create so many of that. The name for this compound, for this, is called stoichiometry. Stoichiometry is the study of, or the calculations involved with quantities of reactants and products in a chemical equation, how they're all related to each other. All right, so let's start with molecular mass. All right, so the molecular mass of a substance is just, so far we already know the atomic mass, or the mass number, and the atomic mass. The atomic mass is just the weighted average that we can find from the periodic table. Carbon has an atomic mass of 12.01, oxygen has an atomic mass of 16.00, etc. So the molecular mass then, as you might imagine, is just the sum of the atomic masses of all the atoms in a molecule. So let's look at an example, chloroform. So chloroform has the formula CHCl3. It has a mass of 119.37 AMU. So let's look at that. All right, there's one carbon. Carbon is 12.01. There's one hydrogen. Hydrogen is 1.008. So 1 times that, and there's 3 chlorines. Each chlorine is 35.45, and so it's 106.35. If we add all these together, we get 119.37. I just want to give you a little heads up. At least use 1 decimal place when you are making atomic masses, when you're doing your calculations. 2 is better, but at least use 1. Don't round. I know carbon, carbon 12, okay, you can round that one. Hydrogen 1, you can round that one. Oxygen 16, obviously you don't even have to round that one. But then, like when you get to like chlorine, 35.45, if you round that to 35, you're going to start making some major mistakes. So always at least round to 1 decimal place. All right, let's look at another example. Now, remember I said earlier that actually ionic compounds are actually not molecules, they're formulas. So we can also define the formula mass of a substance, and it's just the sum of the atomic weights, or the atomic masses, of all the atoms in one formula unit. So if it's molecular or ionic, a lot of these molecular mass and formula mass often get confused or kind of merged into one. I would say I'm guilty of that. Most of the time, actually, I often use the word molecular weight instead of molecular mass. So just keep that in mind. They kind of all mean the same thing. Technically, formula mass is for an ionic compound. Molecular mass is for a covalent compound. They kind of mean the same thing, and oftentimes weight is interspersed with mass, and we know the difference, but they tend to be together. So, for example, one formula unit of NaCl has a formula mass of 58.44 AMU. Okay, so we see 1 sodium is 22.99, 1 chlorine is 35.45, so 58.44. All right, so again, like I said, AMU is not a very useful, because it is kind of meaningless. It's kind of a meaningless unit. I mean, it's not totally meaningless. It has a definition, and we know that a mole, AMU is equal to something times 10 to the minus 24 grams. But it's not anything we can get our heads around, and it's not anything we can use in everyday life. So, here, like I said, one carbon atom weighs 2 times 10 to the minus 23 grams because it's about 12 AMU, and bringing that in is such a tiny number. We can't weigh this. Calculations can be really annoying because we have to use exponential notation. But most of all, we can't get our heads around it, and it's not very useful in everyday lab. So the mole is a definition. So somebody way back when defined the mole as technically the number of carbon atoms in exactly 12 grams of pure carbon 12. So if I only had carbon 12, so not the isotopes or the weight, the average, but pure carbon 12, and I weighed exactly 12 grams of it, and I could count the number of carbon atoms that were in that 12 grams, which I can't, but if I could, that would be 1 mole. There are ways they have, of course you obviously can't see atoms, but with electron microscopes and different things, there's ways to get at this number, which is what they did. But anyway, a mole equals this number. So if you were to count the carbon atoms in 12 grams of pure carbon, you would count 6.022 times 10 to the 23rd atoms. And this is called Avogadro's number. It's also called a mole. So the masses of 1 mole of every different element are different because the masses of each individual atom are different. So even though it kind of came about because of carbon, we can relate it to any element. So keep in mind that Avogadro's number is just a descriptive number. It's an odd number. But it's a descriptive number, just like a dozen or a gross of something or a ream of paper, something like that. We know a dozen eggs means that there's 12 eggs. That's descriptive. If you say a dozen, you know that means 12. A ream of paper means you have 500 sheets of paper. A gross of any item is 144, 12 times 12. We probably don't use these very often, but clearly you use dozen. So in the same way, a mole of iron atoms then is 6.022 times 10 to the 23rd iron atoms. That's just a description. If we have a mole of water molecules, then we have 6.022 times 10 to the 23rd water molecules. Again, this number is really not very imaginable or useful, but still you'll see that it's going to make a big difference in our calculations. So just to play for a second, how big is a mole? How big is that number? If we took 1 mole, 6.022 times 10 to the 23rd marbles, and if we had that many, we could cover the whole Earth to a depth of 50 miles. That's a whole lot of marbles. 1 mole of pieces of paper stacked up would reach outside the solar system. Such a big number. If you had a mole of pennies and you gave away $1 million, or in other words, 100 million pennies, a day to every person on Earth, it would take more than 3,000 years to distribute the money. And here it is written out with all the zeros. If you think about it, we've got, these are the thousands, and then the millions and the billions and the trillions that we can't even get our head around, and the quadrillions and the pentillions, and we're in the hexillions, whatever the heck that means. But anyway, it's a very, very large number. But the key thing here is that the molar mass of any substance is just the mass of 1 mole of that substance. So that's That's the definition, molar mass. So if I have 1 mole of anything, it's equal to its molar mass. Sometimes we'll use the term atomic mass if we're just talking about atom. Like I said, sometimes we'll use the term molecular weight or molecular mass or molar mass. They all mean the same thing. Just like formula mass also will mean the same thing too. So they kind of all mean the same thing, but molar mass or molecular weight, probably I would say that's the term I use most of the time. It's just the mass of 1 mole of any substance. Well, like we said, carbon, 1 mole of carbon is 6.022 times 10 to the 23rd carbon atoms, but it also weighs 12 grams, which is its atomic weight. So for any substance, the molar mass in grams per mole, that's the unit, grams per mole, is it numerically equal to the molecular or the formula weight or the atomic weight in AMU units. So 1 mole of any element weighs its atomic mass in grams. For example, if I have a mole of sodium atoms, I have 6.022 times 10 to the 23rd sodium atoms, and it will equal 22.99 grams. If I have any compound, then it's equal to its molecular weight or its formula weight. So again, for example, if I have a mole of water molecules, I have 6.022 times 10 to the 23rd water molecules, and they will weigh 18.02 grams, the molecular weight of H2O. So now that we have this, we have a new conversion factor. We know 1 mole equals a particular mass. And so we can calculate, we can go back and forth between mass and moles, which I know at this point you might say, well, why bother? But when we start getting to chemical equations, we can see that everything is related in terms of moles. And so we really have to use this, this idea of moles throughout chemistry. So it's the only way that we can do it. So if we want to convert moles to mass or mass to moles, we know that 1 mole equals the atomic weight for an element or the molecular weight for a compound. So it's a conversion factor, right? If we have 1 mole of aluminum, that means we have 26.98 grams of aluminum. If we have 1 mole of sodium hydroxide, we have 40 grams of sodium hydroxide. Sodium 23 plus 16 plus 1. So we can convert back and forth. So let's say we have 100 grams of iron, something we can easily measure in the lab, but we want to know what that means in terms of moles. How many moles is that? So we know the atomic weight or the atomic mass of iron is 55.85. Where did I get that? I got that from the periodic table, 55.85. So how many moles of iron is this? Well, now that we know our conversion factor, we know that 1 mole equals 55.85 grams, we can set up our conversion factor. So I'm starting with what I know, 100 grams of iron. Get my pen here, 100 grams of iron. This time I want grams in the denominator because it will cancel. And I know that there's 55.85 grams for every 1 mole. Remember that the mole is always equal to 1. 1 mole equals the mass in terms of grams. So, sometimes the 1 will be on the bottom, sometimes it'll be on the top. So if I take 100 times 1 divided by 55.85, I get 1.791 moles of iron. Notice that sig figs, I started with 4 sig figs. I used 4 in this term, so I'm keeping 4 in my answer. In the same way, I can use the conversion factor in the other way. So let's say I have a liter of air, and that air contains 9.22 times 10 to the minus 4 moles of argon. I want to know what the mass of argon is in that liter of air. So I look up the atomic weight of argon. Argon is just an element. So I look up argon. Argon is 39.95 grams is equal to 1 mole. So again, I set up a conversion factor. I start with what I know. 9.22 times 10 to the minus 4 moles of argon. This time grams is on the top because that's what I'm trying to, what is its mass? I want to know its grams. So moles will cancel, so I put 1 mole in the bottom and the mass in terms of grams. So if you line up your units and then make sure you put 1 with the mole and whatever the mass is with the grams, you should have these set up right. So 9.22 times 10 to the minus 4th times 39.95 gives me 0.0368 grams. I started with 3 sig figs. I actually used 4 in this calculation, but I want my answer to compare to my original, the number that was given, so I'm keeping 3 sig figs in my answer. Okay, so conversion factor. So that's kind of why we learned how to do it earlier. We're going to use it a whole lot more. If you have any two things that are equivalent to each other, you can convert from one unit to the other by using that conversion factor. Because remember, this is really a kind of like multiplying by 1. These don't look alike, but they're equivalent to each other. Okay, so we have the same kind of thing for molecules now instead of atoms. So the same method applies if we're talking about a compound or a molecule. So let's look at this example. Vitamin C is a compound with a molecular formula C6H6O6. The recommended daily dietary allowance for vitamin C for children is 0.0250 grams. So that would be just for sake, let's see, that would be for, if we divide by 1,000, that would be 25 milligrams. So it's 0.0250 grams. What is the amount in terms of moles? Okay, so the molar mass is given to you, 176 grams per mole, but let's remind ourselves how we get that. We've got 6 carbons, and each carbon has a molecular weight of 12.01, so that's 72.06. We have 8 hydrogen. I still tend to use the 1.008. I guess you could technically round up, but let's just use that for now. And that gives me 8.06. And then I have 6 oxygen, 16.0. If you use more decimals, like 15.9996 or something like that, but 16.00 is probably fine. And that's 96 grams. So if I add that together, I get 176.12. Now, technically speaking, if I put the units as AMU, I would be correct, but probably the better units now that we know is grams per mole. That means that there's 176.12 grams in 1 mole of this substance, so grams per mole. All right, so that's where that came from. And now we start with what we're given, 0.0250 grams of vitamin C, and we multiply by our conversion factor this time because we have grams here that we're trying to get rid of. Grams goes in the bottom, and moles will be our answer. That's so it's in the top. 0.025 divided by 176.12 gives me 1.42 times 10 to the minus 4 moles of vitamin C. Again, 3 significant figures here. I used more than that here, but that's fine. At least 1 decimal, but 2 is good. And then I leave 3 significant figures at the end. We can also have a little fun. It's not very useful, but we can still do it because we know it. Remember that if we have 1 mole of any compound, well, let me start here. If we have 1 mole of any element, it equals its atomic weight in grams, and it equals 6.02 times 10 to the 23rd atoms. If we have 1 mole of any compound, we know that it's equal to its molecular weight in grams, and there are 6.022 times 10 to the 23rd of those molecules in that compound. So we can actually use any of these 3. All of these 3 are equivalent to each other, so we can use any of these 2 as a conversion factor. So suppose we have 3.46 grams of hydrogen chloride. How many molecules will there be in this 3.46 gram? Okay, so now we know our conversion factor is, we know 1 mole, but in this case we don't care about moles. We want to convert from grams to molecules. So we know that 36.45 grams equals 6.022 times 10 to the 23rd molecule. So I can make that my conversion factor. 3.46 grams. There's 36.45 grams of HCl for every 6.02 times 10 to the 23rd HCl molecule. So if I, this was, well, okay, so we started with 3 sig figs and we end with 3 sig figs. 3.46 times 6.022 times 10 to the 23rd divided by 36.45 gives me 5.71 times 10 to the 22 HCl molecules. So we can figure that out. Here's another fun calculation, not really, but we can do it. How many sodium atoms will you consume if you eat 1 serving of potato chips? I looked up on a particular potato chip bag and I found out that 1 serving has 190 milligrams of sodium. So let's say we have 190 milligrams. How many sodium atoms are you actually eating? All right, so what do we know? We know that sodium is 22.99 grams equals 1 mole equals 6.022 times 10 to the 23rd sodium atoms. So there we go. Those are equivalents. Now, a lot of people might want to convert from grams to moles and then moles to atoms, and that's fine. You can do it in 2 steps. But as long as all 3 of these things are equal, you can take any 2 and use them in your conversion factor. Now, be really careful with units. So notice that my molecular weight is in terms of grams per mole, grams. So before we can do anything else, we have to convert our units to grams. So we're going to have to convert 190 milligrams to grams. And remember, there are 1,000 milligrams in 1 gram. All right, so 190 milligrams divided by 1,000 means we have 0.190 grams. So now we've got grams. If you want to show this, if you just know that you have to move the decimal 3 places, that's fine. 0.190 grams. Now I'm converting, actually I don't need to do this step, but I've got 22.99 grams for every 1 mole. And so I know that I have 8.26 times 10 to the minus 3 moles of sodium. And then if I take that and multiply by 6.022 times 10 to the 23rd atoms of sodium for every 1 mole, the moles will cancel, and I'll have 4.98 times 10 to the 21 atoms. Like I said a minute ago, if I wanted to, I could have just started, let's do that here, 0.190 grams of sodium times 6.022 times 10 to the 23rd atoms for every 22.99 grams. So this would just be 1 step, grams cancel, and I would get the same answer, 4.98 times 10 to the 21 atoms. So not very useful, but you can do this for your next party trick. You could say, do you know how many sodium atoms you are consuming when you eat those potato chips? Of course, who can stop at 1 serving? I'm not sure. All right, let's take it, let's do one more example. And we're even going to take it a little step further. So let's say we want to bake a cake and we need 250 grams of sugar. We're just going to assume sugar is sucrose, all sucrose, which it probably is, but let's just make that assumption. Sucrose, C12H22O11. All right, so before we do anything, let's go ahead. Well, okay, here's our question. How many moles of sucrose will be in this cake if that's the only sucrose in there? So the first thing we need to know is what is the molecular weight. So let's calculate that. So there's 12 carbons, 12 times 12.01. There's 22 hydrogen. Here I did did round it to 2 decimals, 22.1.01, and then 11 oxygens. So here's my molecular weight for sucrose, 342.34 grams per mole. All right, I have 250 grams of sucrose, and I know there's 342.34 grams for every mole. So I put grams on the bottom, so they cancel, and my answer will be moles. 250 times 1 divided by 342.34. 3 sig figs, 0.730 moles of sucrose. All right, what's the next question? How many molecules of sucrose is this? Well, I can take the 0.370 moles of sucrose, and there's 6.022 times 10 to the 23rd molecules for every mole. So again, my moles will cancel, and I'll have molecules. Oops, don't count it out, just underline it. Molecules, 4.39 times 10 to the 23rd molecules. All right, I have one more question for you. How many oxygen atoms, if we're just counting just from the sucrose, we're not worried about any other oxygen atoms in the cake, but if I have 4.39 times 10 to the 23rd molecules of sucrose, how many oxygen atoms will I have? All right, well, this one, some of you might get right away, but others may not, may need a little bit of thinking on this. Before I answer that question, let me ask you this. If I have a bunny rabbit, if I have one bunny rabbit, how many ears do I have? I have 2 ears. So I could say I have a bunny rabbit, or I could say I have 2 ears. Of course, if I have 2 bunny rabbits, I have 2 ears. 4 ears, 2 bunny rabbits, 4 ears. So they're equivalent to each other. Actually, so in this case, because I have a molecule, for every one molecule, I have 11 oxygen atoms. So there'd be 11 times the number of molecules of sucrose. So 4.39 times 10 to the 23rd molecules, there are 11 oxygen atoms for every sucrose molecule. So there's 11 times as many oxygen atoms. So now let me do one more, since let's see if I have a little bit of time. I mean, a little bit of room on here. What if I asked you how many, go up here, and I say, okay, I've got 0.730 moles of sucrose, and then I say, how many moles of oxygen from the sucrose do I have? That's a different question. So notice this is how many moles of oxygen atoms, and this is how many actual oxygen atoms. So actual oxygen atoms, how many moles of oxygen atoms do I have? Well, I could take this number, 0.730 moles of sucrose. Let me go back to my bunny rabbits first. So if I have 2 bunny rabbits, I have 4 ears. There's 2 ears for every bunny rabbit. So let me ask you this question. If I have 1 dozen rabbits, how many ears do I have? Well, probably many of you said, 24 ears. But couldn't I also say, if I have 1 dozen rabbits, I have 2 dozen ears? Again, because for every 1 rabbit, I have 2 ears. So if I have a dozen rabbits, I have 2 dozen ears. I have 4 dozen paws. I have 2 dozen eyes, and blah, blah, blah. Yeah, I can make that. So I could do the same thing here. For every mole of sucrose, so for every sucrose molecule, I have 11 oxygen atoms. For if I had a dozen sucrose molecules, I could have 11 dozen oxygen atoms. And if I have a mole of sucrose, I can have 11 moles of oxygen atoms for every mole of sucrose. So that's another way that this question might be asked. So if I have 0.730 times 11 gives me 8.03 moles of oxygen atoms. So I just want you to be really, really careful about what they're asking for. In this case, I was asking for how many moles of sucrose. How many moles? How many moles of oxygen atoms? In this case, 11 moles of oxygen for every 1 mole of sucrose. Just like I said here, there's 2 dozen ears for every 1 dozen. You can use the same ratio. Now here, it wants to know how many actual oxygen atoms. In this case, I take the actual molecules and then I have to multiply by 11. So there's a lot of oxygen atoms. I could actually take this, then 8 moles of oxygen atoms, and multiply by 6.022 times 10 to the 23rd and get the same answer. Anyway, a lot to think about.